Bonjour, mesdames et messieurs. Je suis enchanté de être ici dans ce congrès et je voudrais parler souvent français. Heureusement, mon français n'est pas assez bon. Je dois parler en anglais. Je suis désolé. Good morning, ladies and gentlemen. My goal today, I have two broad goals in the talk that I am about to give. The first is to provide some general reflections on the concepts of both continuity and discontinuity that are potentially useful in thinking about rivers and river systems. I'm then going to turn and consider the type of discontinuity that is really at the heart of this conversation that we are having over these days, and provide some insights, if you will, from recent studies on dam removals, largely in the Pacific Northwest of the United States. Hopefully these insights will also be of some use to you as you think about the general problem of restoring rivers by removing barriers. So let me begin with a broad definition, which is perhaps a little different than the one that many people have in their heads about what constitutes continuity. I'm going to use continuity as reflecting a process or a state that does not change abruptly over either time or space. And this is a little bit different perhaps than the way most people think of it, or it's been used in this room recently, where the continuity primarily focuses on movement of sediment and water and such. But I think you'll see where I'm going with this, this use of the term continuity. So in this sense, continuity reflects processes, dynamics, states of systems, not just rivers, that do not experience abrupt change. So it speaks directly to the famous statement by the American geomorphologist J. Hoover Mackin, who spoke about the graded river as being one in which over a period of years the slope of the channel is delicately adjusted to provide just the right gradient for the transportation of both the water and the sediment. And it's this concept of continuity as a progressive change, an evolutionary change without abrupt transitions, that also underlies things like our notion of succession, our early Clemensian succession from pioneer species to forests, as being a gradual transition, a continuous suite of changes over time. We pick this up again in our own notion of our own succession as primates, from lower primates to presumably higher primates. And perhaps the most obvious example of this is the river continuum concept, which was put forth in the 1970s as a way of explaining the kinds of transitions that occur down a river system in a downstream direction as an orderly passage of different organisms, different gills, different species as the river progressively becomes larger and larger. So these concepts are deeply embedded in our notions of how natural systems in general and river systems in particular work. But that's not the only thing that we need to be thinking about when we think about rivers. There is also discontinuity. And discontinuity is not something, it is not a situation where continuity is good and discontinuity is bad. In fact, discontinuity, which can be defined as the absence of continuity, or perhaps more precisely, as processes, states, conditions that do experience abrupt change over either time or space, is also a part of our river systems. And it is, so we cannot understand rivers without conceptualizing both them as reflecting continuity and discontinuity. The most obvious examples of discontinuity in river systems, perhaps, is provided by midpoints, abrupt changes of the channel's gradient, as you see here at waterfalls. But this is not the only example of discontinuities. There are many naturally occurring dams and barriers that develop in river systems, in part as a result of material, perhaps lava flows, as shown over here on the left, or landslides that move into the river channel and actually obstruct the flow. This is a part of river channel dynamics. And there are even biogenic examples of discontinuities as created by organisms such as beavers. So these are part of our river systems, but we can take an even more in-depth look and observe other examples of discontinuities. The abrupt changes that occur as different sequences of channel units, pools, riffles, bars, cascades. The river, in many cases, is made up of these sequences of abrupt transitions in form, morphology, and process. At the somewhat broader scale, we have reaches, individual sections of river that may extend for hundreds of meters or kilometers that have distinctively different characters. Broad alluvial reaches interspersed with bedrock controlled reaches. And so these features introduce discontinuities, changes, very abrupt changes in channel function and channel behavior, and ultimately in channel evolution. So we have abrupt discontinuities in channel form as viewed in the planform as well, where as a result of floods or avulsions, channels can rapidly change their shape and form. So all of this is by way of saying then that these are aspects of the channel system that need to be recognized along with continuity. And it's not just channels. We have other examples drawn from ecology of discontinuities. We have evolutionary sequences that are examples of punctuated equilibrium. This is where rapid radiation of species occurs at a particular point in time. We have disturbances that can occur, such as fires or windstorms, such that change the dynamics of individual stands. And we have patches that represent abrupt transitions between vegetation assemblages over relatively small spatial scales. So all of these are embedded now in the natural world. And so what I'm really proposing here is that we need to be conceptualizing continuity and discontinuity at the same time. We need to be seeing both of these as attributes of river systems. And we need to be thinking about our management not as favoring one or over the other, but as thinking about how they both occur and where appropriate actions to promote either continuity or discontinuity occur. Having said that, I want to turn to the subject that many of us have been talking about over the last few days and consider the issue of how dams and dam removal play off of these general concepts of continuity and discontinuity. And it should not be a surprise to anyone in this room that there are many, many dams out there. This is from a database by the Japanese scientist Ishidiara, who looked at the development of dams across the globe starting back in the 1700s. And what jumps out from this animation is that there are areas of the world where there are many, many dams, and then there are areas where there are not. In a sense, another kind of discontinuity. But certainly in Europe, certainly in the US, certainly in Japan, certainly in parts of Southern Africa, and now increasingly in China and India, the world is full of many, many dams. And that has prompted as all of you are familiar with, issues and concerns about, do we need all these dams, and if not, how do we take them down? So the issue of dam removal has emerged as a response to this broad development of this fragmentation of our river systems and the associated changes in processes that accompany this fragmentation. However, as you may have gathered, certainly from the talks both today and yesterday, the removal of dams is very deeply embedded in a cultural context. And so the reasons why we take dams down is not universal. And in fact, in the United States, I think as Colleen has already introduced, there are a set of drivers, very much as there are in France, but the drivers are not entirely the same. For example, we have aging infrastructure that is no longer serving useful purposes and poses, in many cases, a hazard to safety. And there are laws that require dams to be removed if there's a public safety issue involved. We have issues that involve the relicensing of power dams that are also being played off against the deregulation of the power industry in the United States. This has provided what might be called a policy window, that is a time when dam removal can be considered as part of the relicensing procedure. Many of the time this is driven by economics, as we saw yesterday in our work groups, and the economics in turn are being affected by many of our environmental standards. So we have strict environmental laws about maintaining threatened and endangered species. Dams have to be upgraded during licensing procedures to provide that level of protection. If they cannot, if this cannot be done economically, then the dams are often retired. So that's the context for understanding a lot of dam removal in the United States, on top of which we have the issue of environmental symbolism. That is, taking dams down has become a way of expressing our good intentions towards the environment. And I think that is not a subtle thing. I think that is a major driver as well. So there have been a lot of dams taken down in a lot of places. And what I'd like to do in my remaining time is to reflect upon some of the lessons we've learned from having taken dams down. To place these lessons about dam removal into a broader context, there has been over the last, let's say, the last 100 years, quite a bit of scientific study around the impacts of dams on rivers. And so these studies, with the timeline shown on the top, these scientific studies have ranged from case examples of individual dams throughout the last 100 years. There have been, in a sense, syntheses of studies of multiple dams, in a sense, stepping back from the case studies and asking what can we learn from assemblages of case studies. There has been the development of conceptual frameworks for understanding dams and their effects on the river. And most recently, there has been the development of analytical and mathematical models to help predict what the effects of dams are on rivers. If we think about dam removal within this context, and that's sort of what's highlighted here in the upper corner, dam removal has largely occurred within this window, but very much the same pattern of scientific investigation has occurred. As dam removals have occurred, which have occurred actually since the early 1990s and even earlier than that, there have been individual case studies of individual dam removals. There is the recent emergence of synthesis work to try to bring together the lessons learned from these multiple case studies, and I'll speak about these in some detail. There have been the development of conceptual models that can help us at least conceptually predict what is likely to happen, and quite recently, there have been new mathematical models specifically for predicting the geomorphic effects of dam removal. And my emphasis here will be primarily on the geomorphic effects, but I'll speak briefly about the biological effects as well. So what has this rich set of studies given us? And I'm going to draw here on some recent examples of dam removals from the Pacific Northwest. Hopefully these lessons will be more general than just the geography of where they have occurred. The first lesson we've learned is perhaps one that will strike nobody as a big surprise, which is that a dam is not a dam is not a dam. And a dam removal is similarly different depending on the nature of the dam, the nature of the river on which these dams are found. Perhaps the most obvious distinction is that depending on where a dam sits in the landscape, it has different effects on the river system, whether it's the effects on the flow, effects on the sediment regime, effects on the temperature regime, effects on water quality and chemistry. So the general model, and I think I saw some similar examples of this yesterday, is that we have these primary variables here of interest: flow, sediment, temperature, chemistry, and that the dam influences these in different ways. The effect of the dam is to may change the morphology of the channel downstream. It may change the water quality downstream, and it hence may change the biota downstream as well. The second lesson is, again, one that seems fairly obvious, but I think it's an important one to consider. Dam removals vary dramatically depending on whether you're taking off large dams or small dams. And I'm arbitrarily defining large dams as dams larger than about 15 meters. Virtually all the dams I've seen at this conference in France fall in the small dam category, less than 15 meters. In many cases, these are less than 5-meter high dams. And the reason why this distinction is important is that in the case of large dams, typically the reservoirs behind them are only partially filled with sediment, and typically with large dams, they have to be taken down in stages. Small dams can be taken down very quickly and are often filled with sediment, which has lots of implications for the downstream reach. This is a time series along the x-axis of dam removals, primarily in the United States, showing the volumes of sediment that have been released as a consequence. And I bring your attention to the fact that this is an order of magnitude scale, so these are all multiples of 10. Most of the early dam removals were of this sort, were only 1,000 cubic meters, 10,000 cubic meters of sediment were being removed. I heard numbers at this conference in which the volumes of sediment were in the hundreds of cubic meters. So most of the French dams fall in this category here. But over time, over the last 10 to 20 years, the volumes of sediment released have now extended to include dams that are hundreds of thousands, and in the case of the Elwha dams, millions of cubic meters. And these have very different effects. The scaling effects from from different size dams, different volumes of sediment released are rather pronounced. So that's an important lesson. Another important lesson that's come from looking across this range of dam removals of different sizes is that we've learned that typically, even for large dams, the reservoir sediment is moved out very quickly. So these are graphs of time removed in days since dam removal for the percentage of sediment stored for different dams. And what we've learned from this is that the rate at which sediment is removed from the reservoir by the river depends on, first, how the dam is removed, whether it's removed in stages or all at once. Secondly, what the nature of that material is. Is it fine sediment, fine-grained material like silt and sand, or is it coarser material like cobbles and boulders? And these have different trajectories as a consequence of this, but in almost all cases, within 1 to 2 years, and sometimes only a matter of months, the material that was stored and represents storage for many tens of years of accumulation is quickly evacuated by channels. Rivers are very good at removing stored sediment under these circumstances. Another thing we've learned is that the fate of this sediment varies in terms of the size of the material. So that, for example, for the same dam removal shown here, we can do a sediment budget and trace the sediment that was released when this dam came out. This is looking at the pattern for the sand that came out. This is looking at the pattern for the gravel that came out. And in a nutshell, the sand rapidly traveled far downstream, many tens of kilometers downstream, very rapidly, in a river that had a relatively high transport efficiency. The gravel and the coarser material ended up very close to the dam itself, was deposited just downstream. And this is a general lesson that we've seen in many other cases. So for example, here are different small, relatively small dams showing the profile immediately downstream of where the dam stood. And you can see that the coarse sediment very quickly fills up these pools, very quickly creates bars just downstream. So the coarse sediment has a local impact, whereas the fine sediment tends to travel much further distances. It can travel all the way down to larger river systems or even the ocean in some cases. So thinking about dam removal requires us to think about what is the fate of this sediment, where will it go, and how fast will it get there. I'm almost done here, but I wanted to mention the biological response as well, because of course this is something that many people, the ecological community, is very concerned about. And what this graph is trying to show is that if you have a river that has a condition here, so the y-axis shows improving river condition in the up direction. So we imagine that the initial river condition was something like this prior to the dam. The dam condition is down here. There is very often an immediate decrease in river condition immediately following removal as a consequence of the disturbance to the channel, to the sediment, and other factors. And that this may recover following different trajectories. And the recovery now is not just of the sediment, but of the organisms themselves. But the biological systems tend to be more complex than just understanding the sediment alone, because we may have a recovery trajectory that results in movement of fish that were previously impeded from movement, but it may also degrade as a consequence of movement of invasive species, or the reintroduction of species that were not present when the dam was there. So the biological systems are much harder to predict, and the models to predict them are much less immature. Let me just end with a few broad comments. One of the things that these lessons from multiple examples of dam removals has given us is some confidence in being able to predict prior to removal what the system, how the system will respond. We can begin to predict, for example, how quickly sediment will come out of the reservoir, what the different types of sediment will do, and how, therefore, the character of the sediment deposit will affect the outcome of the whole dam removal. So we begin to develop what I'm calling here hierarchies of control. We know what's more important than what, and this gives us, even without running mathematical models, it gives us good insight and some confidence in saying to managers, here's what's likely to happen. So we can do this for the upstream reach, and we can do this also as well for the downstream reach. We know that the grain size of the sediment that's being released has a lot to say about how far things will go, where the water quality will be diminished, and so forth. And we know how this may play out against different types of channels. So we have a level of predictive capacity that we did not have even 10 years ago, and I think that's a good thing. But let me just conclude with an even broader point, and it's one that was hinted at by a number of the talks. Dam removal sits within a cultural context, and both dam removal and dam construction are fundamentally cultural, technical enterprises. If you look at the history of dam removal, both in France, as we heard from Regis earlier, or as we heard from Colleen earlier, we have a history of building dams as a way of, in a sense, taming nature, getting nature to work for us, to produce power for us, to produce food for us. And dams represented a mark of our progress and our ability to control our environment. And this takes us through the 1930s, the 1960s. This is a picture from in San Francisco of Shasta Dam, a symbol of progress. But then starting in the 1990s, we have begun to question, do we need all these dams? And so we have our former Secretary of the Interior, Bruce Babbitt, swinging a symbolic hammer to break the dam. Okay, so the story changes, the cultural context changes. But we're not done yet, because we are facing a changing world. We are facing a changing world of a climate that is changing, in spite of what our American president says. We are facing a world that may need low carbon energy sources, and so we may have to reconsider dams as potential, and we may need to consider them as ways of mitigating effects of a changing climate on river systems, on the flow system, and on the temperature system. So we should be careful not to promote dam removal indiscriminately, but to think forward and to anticipate what the stories are likely to be in the future, what the cultural context is likely to be in the future, so that our actions to restore rivers provide us with river systems that we want to live with far into the future. Merci beaucoup de votre attention.